All right. So let's finish up what we were discussing near the end of class last time. I'll review a little bit of where we were going. Um, I would say the stuff, well, obviously everything we talk about is gold and you should have all of it committed to memory, whatever. But probably the next 15 minutes is pretty important and connects some dots for us. Um, we're going to be talking about variable scope again from a little bit different angle. Remind me, what is variable scope? When we say the scope of a variable, what are we talking about? Not the mouthwash. So, what's the scope of a variable? Yeah. So where was it born and where do we have access to it? And that changes depending on where it was brought in, where it was defined. All right. And that's going to be an important thing here that's going to explain what's going to initially appear like a weird behavior. I would probably uh, emphasize that almost always, if you, I'm going to throw almost in there because there might be some special cases or something, but almost always, if you see that there is a weird behavior happening and you don't understand why, there's probably a very clear logical reason for it. You're just not thinking down that path. All right. And this is a good example of this. What we're going to look at today is something that has tripped up many developers over the years. And the answer makes perfect sense once you see it. But initially, it's a head scratcher, and you might chase down a bunch of different rabbit holes until you finally uncover it. So let's get ourselves into the position of the problem first, okay? So just as a review, last time we introduced arrays, right? So arrays are kind of like strings in that they hold collections of the same type of value. Strings hold collections of chars. Arrays hold collections. We could have a char array, which would hold a collection of chars. In fact, that's how old school strings worked. Back in the day, before we had this newfangled string class that makes life easier for us, even though some of you don't like strings very much, trust me, it was way worse before. Um, before we had this string class, if we wanted to store a collection of chars, a string, we would create an array of chars to do it. And it wouldn't have all those extra special functions like the length and stuff like that built into it. We would have had to write that ourselves. Um, but we can hold an array of ints, an array of floats, an array of anything we can create a variable of. And keep in mind pretty quickly here, hopefully today we get to this. Yeah, I think we will. We're going to be able to have an array of something called a struct. And then shortly thereafter, we're going to be able to have arrays of objects that we invent ourselves. All right. Now, pretty quickly here, we're going to be transitioning over to Java, as I kind of promised you. We're gonna kind of keep pushing down um, the C++ route to introduce structs and to initially introduce objects, but we're actually not going to do the objects in C++. We're going to start off there in Java. You're going to see that there's not a huge jump. Almost everything is the same, except we lose the pointer syntax that we've been talking about. But that doesn't mean pointers are gone. I think I mentioned last class that a lot of textbooks say that pointers don't exist in Java, where the reality is in Java, basically everything is a pointer. So it just doesn't give you the special syntax for working with it. So it is really important that you understand the idea of pointers, the idea of memory addresses, and the consequence of those memory addresses. If I give you something that lives in memory up there and it's to another function, so two different functions are pointing to that same place, if they make changes there, that change is felt across all of the different places that have access to that memory space. All right, that's an important concept if we are doing something that we want to have a permanent side effect. It's also an important concept to understand if you specifically don't want there to be a side effect. You need to take the necessary steps to make sure you're dealing with a copy as opposed to the real McCoy. All right. And that'll unfold as we see stuff. But let's get ourselves into the weird position here. All right. So we started off class last time. We wrote kind of our own version of add fractions that worked with, we decided a fraction is a numerator and a denominator. So if we want to add two fractions together, we said, okay, well, I need 4 pieces of information. So we just passed in 4 integers, did our common denominator stuff, whatever. We did the logic to add fractions. And then we got into this position of like, oh, well, how do we return the answer? Right? Because we technically needed to return 2 values, a numerator and a denominator, yet up to this point, we only know how to return one thing. Now, I think back there he had suggested, well, what if we just pass the first couple guys in as pointers and we just we change those values, and so the people outside of here gets their updated fraction. We saw that work. You can do it. So now we're kind of like problem solving by dancing around in memory, right? And taking advantage of it. So we're going to keep going down that path. All right. So in this second thing that we started writing, we're going to write a new version of add fractions. And this one's going to work with fraction arrays. So it's going to take in 2 integer pointers. One's going to be the first fraction, a pointer to the first fraction. The other one's going to be a pointer to the second fraction. And we've advertised that we're going to return a int pointer, the new fraction. All right. So let's go down that path here, and then we'll see our issue. Let's see. Let me just gut this a little bit. Okay, so we decided we're going to have here's our 2 fractions. Each of our fractions holds 2 elements. Bucket 0 we've decided is the numerator. Bucket 1 we've decided is the denominator. And pay special attention to we've decided. We haven't put any of that policing information into our code. We have to remember that we intend to store the numerator in bucket 0 and we intend to store the denominator in bucket 1. Nothing in here is structuring it for us to follow those rules. All right. So let's go down to that function. So here is our add fractions array. This guy's going to take in 2 integer pointers, which are fractions, which are arrays rather, right? Because remember we talked about in the notes, do I have Keynote open here? We drew a picture of our arrays. We updated our example from strings. Mentioned a few minutes ago that strings and arrays are basically the same thing. Strings are an implementation of arrays for collections of chars that can also do some other stuff. In this example, we're looking at integer arrays. So if we create an integer array capable of holding 4 ints, they live next to each other in contiguous memory, that is memory in a row. So if I need to hold 4 ints and each int is 32 bits or 4 bytes, we need to have 128 bits or 16 bytes of data next to each other. We need a plot of land 16 bytes big in order to hold 4 integers on that plot of land. Make sense? All right. So it's important that we remember that arrays live in memory right next to each other because we're going to be doing pointer math here before too long where we walk those arrays manually. So in this example, if I were to create an integer array like this, and I kind of gave you a little foreshadowing last time that this is probably not the way we're going to define arrays moving forward. This is kind of the shortcut version of defining arrays that has a caveat with it that we're going to stumble into here in a few minutes. So if we were to define this and it handed us the base address of 100, that is where the array begins. So the value of F1 here in this example would be 100. It points to the very beginning of the land where the array lives. Bucket 0 of that is at memory address 100. Bucket 1 of that is 1 integer later, 4 bytes later at 104. Bucket 2 is 2 integers later, 8 bytes, 108, so on and so forth. All right. So this is the way things are organized. If we change this to a char array, this would be 100, 101, 102, 103, because chars are 1 byte big instead of 4 bytes big. We were dealing with floats. These would be a little bit more memory. Floats are 32 bits followed by 16 bits for the after the decimal point. So it'd be 48 bits, so on and so forth. arrays give you enough memory to hold however many things of that type you've asked for. All right, but this is how they're organized. All right, so we want to go ahead and add these fractions together. So what we're going to do here is we're going to create a new integer array, maybe called answer. And we're going to build it to hold 2 ints. All right, so now last time we saw that we were able to output the memory addresses of fraction 1 and fraction 2, and they were the same memory addresses as F1 and F2 that we passed in. So we saw that we were dealing with the same memory. All right, so I'm going to go ahead and get rid of those. All right, so the first thing I want to do is I want to figure out my common denominator, basically the same stuff we did in the other example. So the common denominator would be the 2 denominators multiplied together, right? So we'll say int common denom is equal to fraction F1 at bucket 1, which is the denominator of the first fraction, times fraction 2 at bucket 1. So I'm multiplying the 2 denominators together there. Make sense? All right. Now we need to update our, so we'll call this guy new numerator. And the new numerator is we're going to cross multiply. So we're going to say this is fraction 1 at bucket 0 times fraction 2 at bucket 1 plus fraction 2 at bucket 0 times fraction 1 at bucket 1. Slide this over here. All right, so we're going to take the numerator of the first fraction, multiply it by the denominator of the second fraction, add that together with the numerator of the second fraction times the denominator of the first fraction. That'll be our new numerator. So then ultimately our answer will be answer at bucket 0 is going to equal our new numerator. Answer at bucket 1 is going to equal our common denominator. And then we're going to return answer. All right. Now, just for testing purposes here, since we're going to be doing several things, let's go ahead and give ourselves a quick function that we can pass a integer array to, and it just displays that fraction for us. So let's just create it'll be void, not going to return anything. It's just going to print some stuff to the screen. Let's call this guy display fraction. It'll take an int pointer as a parameter. All right. So whatever integer pointer we pass in here, we're going to go ahead and see out f at bucket 0, followed by a slash like that maybe, followed by f at bucket 1. All right, so we can go ahead and now call display fraction from down here. So we'll say display fraction, and we're going to pass it answer. We want to print out the new fraction we have, right? All right, so we expect that to give us it's not reduced fraction, but the correct fraction added together. Then we'll go ahead and return that answer, which is returning an integer pointer. So up here where we call add fractions, let's go ahead and give ourselves an int pointer. We'll call it answer again. And then we'll go ahead, let me get rid of this for loop here. Then we'll go ahead and call display fraction on answer. All right, so let's just make sure this is doing everything I wanted to do. All programs begin and end with main. So I just define a variable for how big we want our fractions to be. That's not needed. We could have just put a 2 in here for both of these. So we're defining two integer arrays, each capable of holding two values. We'll go ahead and fill it up. So we're representing the fractions 1/2 and 1/4. We'll go ahead and print out those two things, showing us the memory addresses of those dudes. We actually probably don't even need to do that in this example. We've seen that work, that they're the same values in there. So then we'll go ahead and call our add fractions, passing it F1 and F2, which are integer pointers, right? Because these guys are arrays, and arrays are integer pointers. So even though you don't see the special syntax here, this guy is a integer pointer. And I'm going to show you the alternative syntax that you're probably going to want to use moving forward in a few minutes here. All right, so we call add fractions, patching the result here. Inside of add fractions array, actually, I want to make sure I'm calling add fractions array. Yeah, so make sure you're calling the right version of add fractions here. All right, so we'll go ahead and create our integer array for holding our answer. We'll figure out our common denominator and our new numerator. We'll go ahead and fill our fraction up with the correct numerator and denominator. We're going to go ahead and display it here locally. We should get that 6/8 displayed inside this function. Then we're going to return it. It's going to return right here. Then we're going to display it again. And we would expect to get 6/8 here. We're going to run this. So here is the 6/8 inside of our function, is right here. So let me just give you a little C out here. C out inside function. And then before we display the answer here, we'll call this guy outside function. Go ahead and run this guy again. We see that inside the function, we got 6/8, the correct answer, right? Outside the function, we see nothing. Now let me give you a little bit more evidence before I ask you why. So inside the function here, before I display the fraction, let's display the memory address of answer. All right, so that's going to give us the memory address of this dude right here. Outside of the function, let's also display the memory address of answer, the integer pointer that was returned here. Run this again. We see inside the function, here's the memory address of answer. Here's the value that lives at that memory address, put into pretty print form, right? Outside of the function, though, we did not get any sort of array displayed. And we see that the memory address of answer out here is 0. Why? Remember, I mentioned that this is something that many experienced programmers get stumbled up on, and the explanation is perfectly logical and does not deviate from anything we've talked about up to this point in this course. Anybody have a theory as to why it's working out this way? Go ahead. That's it. Down here in our add fractions array, this is a local variable. Now notice it did give us a little warning down here, so it gave us some inside information. Warning, address of local variable answer is returned. Local variable. And as he pointed out, any variable we define inside of a function as a local variable. So this guy's scope lives and dies from line 42 and dies at line 52, the end of that function. It's gone. So here in this function, we are requesting memory from the operating system, enough memory to hold 2 ints. Then we go and do all our stuff. We saw it all worked, right? We got our right answer right here. No problem. We saw this guy had a real memory address. Then we went and returned it. Now, before we actually arrived back at main, though, all the local stuff we defined inside of this function dies and is given back to the operating system. So that means out here, when we receive that answer, this guy received the value of this local variable that lost its value when this function ended. That's why when we get back out here and we go to print out the memory address, we see its address is 0. Basically, it means it doesn't have an address. It's empty, unused pointer. Operating system has already reclaimed that memory for future use. So effectively, we've lost our answer, right? So when we go to display the fraction, now, one thing you would get, I'll just kind of give you a, we wouldn't get it in this example, but we could get it in this example reasonably. Something you've maybe seen as you've done some of your C++ stuff. Have any of you, especially as we've gotten into some pointers, have any of you seen an error that says segmentation fault? You seen that guy yet? So if you're ever programming in C or C++ and you get an error that says segmentation fault, gives you no additional information beyond that, 100% of the time, something has gone wrong with your memory. One of your pointers disappeared. You tried to access memory you don't own, whatever it is, it's a memory error. Okay. So in any case, we got a couple of warnings here about like, hey, are you sure you want to do this? I'm not sure it would ever make sense to return an address that isn't an address. I'm not sure why one might do that, but so probably that should be an error. Like you probably don't want to do this. We're not going to let you continue, but it doesn't. It gives us a warning. Newer languages would, well, you actually couldn't accomplish this in Java. I'm about to show you that you never want to define arrays this way to protect yourself against these problems. Just because the syntax for defining arrays using this little syntax here seems nice and convenient compared to the alternative, which we'll look at, which I'll try to make look as scary as possible, but it is way better. All right. This shortcut, which I often will refer to as syntactic sugar, they make it look pretty for you, has the consequence of only working when you're using that value only locally in that. Now, that is to say, though, we passed F1 and F2, which are local variables here in main. We passed those into this function here. And they came in and we printed those addresses and saw that the address made it in there. Well, why did it work going that direction, but it didn't work going the other direction? Why did we lose our address when we defined something inside of add fraction array? And we kept the addresses when we defined these variables in main and passed it to add fraction array. Why do I still have the memory addresses of fraction 1 and fraction 2? Why didn't they zero out? Same answer. Variables die at the end of the scope in which they were defined. Program's still running because main is still alive, which means the memory of these guys, which was defined right here, has not been reclaimed yet because main is still running. We've just paused main and gone and started doing something in another function. But this guy's still alive. He hasn't given back that memory yet. But when we went the other direction, when we were inside of our function and that function died, the local variables we had in that function disappeared with it. All right. So that's why we're getting a problem there. Any questions on how we lost our memory address? And that's consistent with everything we've seen up to this point, right? Pointers aren't special in any way in terms of variables. any variable we were to define inside of our function will be gone when the function's over. Now, what if, I'm just going to modify this guy real quick. What if I had said this guy's going to return an int, not an int pointer? And I said something like int a is equal to 7. And then I return a. I'm not going to run this because I'll have to change a bunch of other things here, but would my 7 make its way back to main if I defined that variable locally inside my function and then returned that value? And I'm returning an int. Would I have access to that 7? Would that 7 still be there when I go back to main, or will it have disappeared? I am trying to trick you. What do you think? Go ahead. Okay, nope, it's still there. So then the question is why? So I promise you, if I were to make some manipulations and we were to catch the int in main and then print it out, we'd get our 7. We wouldn't get the nothingness that we have from the pointer. And this goes back to this slide. Passing values to functions. Pass by value versus pass by address. Just like when we pass a value into a function, like if we pass an int to a function, a normal plain Jane int, not an int pointer, what we're doing is we're passing a copy of that value. So any changes we make to it inside that function will not have side effect outside of it. The same thing is true when we return a value from a function. If we're returning an int, we're returning a copy of the value. So even though he's right that my, whatever I name my variable here, a does in fact die at the end of this function, but I've already sent a copy of the value that a holds. A is going to die, but I preserved a copy of it by returning a non-address type, a non-pointer type. So that 7 will still make it out of here. It's no longer associated with this variable a, and we'll catch it inside of main, inside of another variable, and be able to display that 7. Go ahead. It would be passed as a temporary memory address. This gets into how the language is actually built under the hood. When main calls a function, new memory is created for that function. Things happen. When that function dies, there is a handoff, because functions have return types. So there has to be a mechanism in there for a function to hand stuff back to main, right? So to your point, he wants to know, well, if a dies and 7 used to be stored in a, who's holding that 7, right? So you can almost think of it as kind of like a little magical thing that just carrying it over to main and saying, okay, I have this value here. I don't have it stored anywhere, but I'm going to kind of throw it out to you. So I kind of like thinking about it like this, where here's this function. When this guy returns to main, something comes firing out of this. It says, okay, here, catch. And as long as we put a variable in here to catch it, that 7 makes its way into that new variable. But it's kind of in limbo in the middle. But the important piece here is we didn't lose the value because the value was passed as a copy, not an original value that's now disappeared. Make some sense? So again, this is all consistent logic. So it's not like we have special cases for pointers or anything like that. It's all the same stuff, all the same rules that are involved. But as soon as, just like I mentioned before, as soon as you have pointers involved and you see memory addresses and all this stuff, you start getting intimidated. At a glance, things don't look right. You start seeing weird error messages like this that even if you didn't read it, you see warnings, you see these little underscore tilde things, and all of a sudden it's like, okay, I'm not even going to read that because it's intimidating. I'm just going to start changing crap until it works. Don't do that. Always read your error messages, but know that one of the skills you're going to have to build up as a programmer will be your debugging skills. Seeing an error message and kind of, I mean, you see the same error message enough times, you'll start not making that mistake in the first place, but you'll also be able to instantly fix it, right? Okay. Oh, one other thing before I move on to the next step here. As far as midterm grades go, so the way it works for your classes is in Blackboard, we have to set this external grade column. So in here, that's your overall grade, which I know right now some of you have a number in there that you're not happy with. But understand that that grade isn't what ultimately goes into your final grade in Banner when the class is over. So let's assume the class was over today and your final percentage in the class is whatever that overall column says. You would find that the final grade you would get in the class is probably substantially higher than that number would indicate. Okay, so for example, if we were ending the class today and I look at the performance from the midterms and stuff like that, probably scores in like the 50 to 80% range would kind of be in that B to low B range. Probably 80 and above would kind of be in the A to low A range. So a much broader thing. I would probably be telling a little bit of a different story if we were in the 250 class, the next course. But understand, since day one, I told you coding is going to be hard, right? I told you it's going to be a lot of work. And I know it's stressful and all this stuff, but also believe that I know the process. And I've been doing this a long time. I'm not in the business of punishing you for hard work. Okay. So even though you might not like the numbers, understand that I do curve the class with the ultimate goal of I want to encourage the students that have this in them, while maybe getting students who this just isn't their cup of tea or they didn't engage in class to either repeat the class or maybe think about switching majors. So if you consider the range of scores from the midterm, most people on the midterm got either, let's call it 75 or better, or got 20% or worse. There was very little in the middle. So if your grade is in that 50, 60, 70% range, that means that you pretty much knew what was going on. You didn't quite get all the logic put together. It could have been a time. I know there were several people who basically had 100% going on the midterm until they they didn't have time to answer questions 9 and 10 or something like that. Well, that's going to hurt you, right? So understand that I know how it works, all right? You're not going to fail the class if you have a 50% in the class right now. As long as you keep up the work. And I mean, my expectation would be for most of you, if you got a 50 on the midterm, that means you had a clue what was going on. You didn't leave all these questions blank. You just didn't pull it all together probably on most of the questions. I would expect that you're probably going to end up with at least an 80 on the final because you've already gotten to the point you're at right now. We just got to leave you in the oven a little bit longer to keep cooking, and things are going to start clicking for you, I promise. So stick with the process. Don't be afraid of the grade result. I don't fail very many people. I mean, if you fail my class, it's basically because you chose not to participate in the class. You didn't do homework, you left exams blank, or you didn't take exams, that kind of stuff. All right, that makes sense to everybody? I know it's hard. I want you to suffer, but I'm not going to reward your hundreds of hours of work with a big, happy, smiley face F. All right. Now, when you get to the third coding class, if you're still not quite getting it, I'm probably a little bit harsher. So if we were in coding 2 and you were sitting at a 50%, maybe that would be a C or a C minus. Still not failing, but things should have been clicking a little bit by now. So we got to reevaluate where you're putting in there. But it's a process. So understand that I know that, so don't flip out too much. Cool? All right.
So I thought I'm trying to wrap my head around the copy idea. If you scroll down and you define A as the 7, right? You said it makes a copy. When you say it makes a copy,
it didn't make a copy here.
Oh, or
yeah.
Return it.
Yeah.
When you say a copy, do you mean it takes like second memory address and assigns it 7 as.
Correct.
So it does, it gives it, okay.
Yeah, so, and that's kind of that magical thing in the middle, that there's some under the hood process where a function hands control back to main. And in that, the return statement says, I have a payload for you that you're sending back to main, and that payload is holding the number 7, to your point. Yes, in another memory address, because that's where we store values.
And then you clear the original.
But yeah, this A dies. So if we assume A was in memory address 100, at the end of this, memory address 100 has nothing in it. But the value that was stored in A maybe gets thrown into memory address 500 temporarily, as control was handed back to main, and you as the programmer got to decide, am I going to do something with that value? Am I going to catch it and put it into another variable that I can use later? But though the memory addresses of those variables are not related, the value that they hold is, and that comes back to this idea of whether something is passed by value, which you can think of as passed by copy, versus passed by address, which is like, hey, here's the real deal. Any changes that you made. And that's why we saw it work. If we're passing pointers, which is all, if we're passing a pointer, we're always attempting to pass by address. All right. So that's why when we passed these pointers in here, since these local variables here are still very much alive, because main is still cooking. Main got paused, but it didn't die. Okay, so those memory addresses are still very valid memory addresses. The operating system is not taking it back. Therefore, inside of here, we have those memory addresses with the real values that were in there. Nothing's been destroyed. Where we ran into problems is when we created a local pointer inside of here. This guy lives and dies with this function. It was when we tried to return that guy that we ran into the problems of our memory address has disappeared. We put our answer in this perfectly good place in memory that was a local variable, and then it got bulldozed on the way out, and our values are gone. And it was because this guy died. Make some sense? Good. Okay. So for those of you online, what he suggested, well, can't we here? Let's return this back to what I had here, just to get it back to its old condition. Does that get me back? Oh, I need this guy to be an int pointer. Okay. Now we're back to the weird behavior, right? So here's your answer inside the function. Everything's cool. Outside the function, our memory address, this dude has become this guy, and we didn't have the right to read anything from that memory location, so we didn't get our answer anymore, right? So his suggestion was, well, rather than return that value that we know we're going to die, couldn't we just kind of maybe move this guy up here, maybe to a global variable, make it available to the entire program? Now this guy's a local variable to the entire program. He doesn't go away till the program dies. And we have access to it since we defined it here. Its scope is anywhere inside of this file. We have access to it in main. We have access to it in display fraction. We have access to it everywhere. So he was suggesting, well, if we wanted to bypass this problem, and I would say this is kind of a dangerous mentality, but it makes sense. We ran into this problem where our pointer isn't working. So rather than trying to understand why our pointer wasn't working, we immediately looked for a workaround to get the answer we wanted. And yes, that would work, but that's not the right way of doing it. Now, if you're writing a quick little program that you're going to be, it's only going to be part of your life for the next 10 minutes, you're just solving something real quick in code, do it quick and dirty. Just don't worry about scope. Just give yourself global variables for everything, get your answer, move on with life. But a majority of the time you're writing code, you want to follow best practices. And in general, something you'll find in a lot of textbooks is this idea that global variables are bad. Now, I think that's short-sighted. Global variables are often a bad idea. It's often a cop out, kind of like what you're suggesting. It's like, oh, let's just throw it up there so it works. They can often be a bad idea, but sometimes global variables are the, let's call it the yeah, I mean, it really shows its face in like Android programming the most. So in mobile application programming, when you go between different screens of your application, there's a process by which the next screen is launched and a process by when that screen goes away, like you hit the back button or something like that, or you hit OK and it disappears. There's an opportunity to get information back to the previous screen. And most of those things have, so in Android, it's called add extras. You know, they have like this little suitcase that comes with, in Android, it uses these things called intents. I have the intent of launching another screen, and an intent comes with a suitcase that you can put crap into, right? And that survives the loading and the unloading of it. Well, let's assume that you have an application with like 10 different screens in it. Who's calling me here? So let's say you have an application with 10 different screens in it. Now, you could play the game of shoving, and let's say all 10 of those screens need the same 3 values. You could play the game of literally packing copies of those 3 values into every single suitcase for every single screen that's going there. But at some point, this becomes tedious when you could have just thrown those 3 values in a place that's accessible by all of those screens. I think that's a reasonable use of we would call those global variables. When we learn about it, we're going to do it in terms of something called a singleton, basically a class that holds global variables. I think that's a reasonable use. I mean, just like, you know, in real life, when you solve problems, you want to use common sense, right? If I'm just passing 3 values and I have to pack them up tediously 10 different times, or I can just throw them into 3 global variables and move on with life, put it in the global variables. Just make sure you pass it through that logic process instead of just saying, oh, I'll just put everything in global variables. Because you know what? By doing that, I've never run into scope issues. Everything's accessible everywhere. The only problem I run into is having more than one. I want to name more than one variable the same thing, but it was already in the ultimate scope. So it's going to tell me it was already defined. So we might have to have like answer 1, answer 2, answer 3 up in global. But again, it goes right back to how humans solve problems. Use your best judgment, but just make sure you're interjecting logic in that decision making and not just doing something because you like that it worked. Learning something just because it works isn't going to get you very far for very long. Go ahead.
Why is that so heavy?
I would say it's not necessarily less secure. I mean, maybe you can make an argument in some such situations it could be a little bit less secure depending on the type of data, but really it becomes an organizational mess. It's kind of like we go back. Let's see. I think I've talked about object-oriented languages. We haven't really talked about it yet, the details of implementing it, but we had the example of the object-oriented telephone, right, where you had the pile of wires. And then we had the thing that looks like a telephone. Okay. So that pile of wires there, even though we know everything works, we know everything is functional, we look at it and it's just this disorganized mess. And as your programs get bigger and bigger and bigger, the idea of documentation and organization and this thing called encapsulation, which is basically organization, starts becoming more and more important. Okay. Because even though programs right now of like 100 lines long feel pretty, but you've had kind of enough a lot of times for most of you at this point, right? Because 100 lines is a lot of lines when you're having trouble to write the first 3. Okay. But when you get out into industry and you're starting to be part of projects with millions of lines of code, if everything was a global variable, people would switch careers real quick. Make sense? Okay. But I would say that statement is even compatible with what I said the first week of class when I said programming is hard and human beings are used to solving problems the way we've solved them our entire life. And now we have to learn a new way of doing it when talking to a computer. Because even though I'm sitting here and I'm saying that keeping things organized in real life is a good idea, how many of you, is your dorm room currently a mess? Your backseat of your car is currently a mess, whatever. Most of us at some part in our life are lazy, right? Okay. I mean, I drive like a nice, expensive car. The back seat of my car is filled up with soda cans. My wife says I have a hobo living in there. So, but every couple of weeks, I have one of my grad students come over and clean it up. Totally true. All right. Any other questions on this? And these are good questions because I want you to constantly be thinking about this stuff in terms of how should a human being solve this problem? Because that's the job of a programming language, is to synthesize the way we solve problems into a language to allow us to tell this guy what to do. So I'm kind of suggesting maybe try to be a little bit more organized when it comes to your coding than maybe you are in your real life. And I would almost say I'm the living example of that. I would say I'm basically a slob in real life. My wife is basically always cleaning up my messes. Yet with coding, I'm pretty particular about scope, indentation, things that I would not be particular about in real life. So programming kind of has this, you're going to get into trouble if you don't make some effort into doing it. All right. Okay. So we see right now that we have our problem, right? But we have decided, at least for our baby step forward, that we're going to store our fractions inside of arrays because I need to return two values, a numerator and a denominator. And as far as our toolbox goes right now, exists right now, we only have one way of having two values returned at once. And that's inside of an array that has a collection of values, right? And we just are remembering that bucket 0 is the numerator and bucket 1 is the denominator. But in order for that to work in this case, we need what happened to my answer?
Yeah, you still.
Oh, thank you. See, now he's got me doing bad habits. It's okay. All right, so now we're back in here. We'll see we have the same output because we had access to it locally here. We had access to it globally. We had access to it either way, but we have our problem. We want answer to be able to be returnable. So the question is what can we do to make it returnable? Let's go back to our slides here. All right, and I mentioned I'm going to try to make this as scary as possible to make you not want to do it, and then I'm going to tell you really should always do it. Good news is when you get into a newer language like Java, they don't give you this alternative syntax, and they make the scariest way of doing this go away and have kind of a middle ground thing. So when we look at this slide right here, when I define a variable f1 and it's creating this memory stuff, I'm using that shortcut syntax, right? Let me show you the alternative to that syntax. I'm going to say int pointer f1 is equal to. Now I want to hold 4 integers, right? And we decided that 4 integers is going to take, so it's 4 bytes per integer, so 16 total bytes. All right, so I need 16 bytes of contiguous memory. Okay, so I need 4 times whatever the size of an integer is, which we just verbally said it's 4 bytes. Okay. I want to allocate that much memory. Memory allocate, malloc. Before you had malloc, you had alloc. That was in C for allocating memory. All right. So if we go back in here and I update this guy, answer, to be an int pointer, answer is equal to malloc 4 times size of int Oh, from void pointer. Let me just run it and then I'll tell you what's going on there. All right, so now we see we got our answer back. So that one little change made it work. Everybody's good with that so far? Now let's explain why. All right, first of all, let me put the little error message that we just got back in and I'll explain what the problem is. So I'm just going to remove that little piece right there. So any way you cut it, we knew before we were dealing with an integer pointer, even though when we defined our fractions like this, we don't see that special syntax for pointers. We don't see the little asterisk there, but we've seen that this syntactic sugar, this special syntax right here, does indeed produce us a memory address. That's its output. Its output is an integer pointer. All right. So down here, I'm going to say, okay, well, I'm going to go ahead and I'm going to create an integer pointer, but I'm not going to use that shortcut syntax because we saw that that shortcut syntax had some consequences that we didn't necessarily love. So I'm going to create a variable of type integer pointer, and what am I going to put in it? I'm now talking to the operating system directly. I'm saying, operating system, I need to allocate some memory. Malloc, memory allocate. How much memory do you need? Well, I need to hold 4 of something that's that size. And size of int will be 4 bytes. So if I do a cout size of int, oh, sorry. I took the little thing off. I'll still come back and explain that in a second. So there's my 4 for 4 bytes, size of int. If I were to change this to a char, it should now be 1 byte. There's my 1. If we were in Java, this would be 2 bytes, 16 bits for chars because it can hold its Unicode versus ASCII. If I say size of float, okay, so float is still using 4 bytes for its memory because it stores the decimal points in kind of a weird under the hood way. But it is 6 bytes, all in all. All right, but we have this little function here called size of that'll tell us how big something is. If we want to say size of, what did I name my fraction up here? F1. Size of F1 gives us 8 bytes. Why? F1 holds 2 integers, 8 bytes. Make some sense? Okay. Somebody, oh, they're drawing on my screen. That's fun. All right. I don't even know how to undo it. I'm guessing it's something with annotate or whatever, but we'll just let it go. Have some, oh, did I? All right. Good. How do we undo it? There's an eraser?
Just why don't you try and use Command Z?
Because well, I mean, it's a reasonable thing to ask. So I can undo mine, but I can't undo his. There we go. See, now he's just going to put it back in there. It's going to be a competition. All right. So in any case, why did we get this error here? When I say I want to allocate memory and I tell it how many bytes of memory I want to allocate, what it does is it gives me back what's called a void pointer, a generic memory address. Now, in this case, I want a memory address that is of type int pointer. All right, and I'll run it real quick so you can see the error. Invalid conversion from a void pointer to an int pointer. So as it is right now, this is coming out as a void pointer, and I'm trying to shove it into something that is an int pointer. Now I can just change this guy to void pointer if I want. And then that error will go away, but we'll get a new error. We'll get a new runtime error. And the reason for that is when I say, okay, thanks for giving me the memory, I want that memory to be treated as a memory address for integers. Why do you think that matters? Why do you think a pointer to an integer is different than a pointer to a char, is different than a pointer to generic memory address? An address is an address, right? How we navigate through memory to get our values. When we go back and look at this guy here, when it was an int, if I say bucket 0, I'm going to get the very first thing. Really, what am I getting? I'm getting the first 4 bytes from that base memory address. Why is it 4 bytes? Because we know it's an int pointer. If it was a void pointer, we don't know how many bytes we're going to be walking. If I was dealing with a char pointer here, this int would be broken into 4 pieces, because a char is 1/4 the size of an int, right? An int is 4 bytes, a char is 1 byte. So that means if I have stored the number 1 in this memory location, but I tried to access this guy as a char, it would only give me the first 8 bits of that 32-bit value. So if you think of that number 1 currently being 31 zeros followed by a 1, right? That's a 32-bit integer. 31 zeros and then a 1. And I try to access that 32 bits as a char, I'm only going to be looking at the first 8 bits, which is a 0. If I try to access it as a short, I'll be looking at the first 16 bits, which is still a 0, so on and so forth. So that's where we're starting to get under the hood and understanding that, hey, memory is memory. There's nothing special about memory. But when we flag an address as a certain type, it dictates how big of a step we take when we move from bucket 0 to bucket 1 to bucket 2, so on and so forth. You know, 1 step from bucket 0 to bucket 1 in a char pointer is 1 byte. It's a step that's 1 byte big. But going from bucket 0 to bucket 1, if it's dealing with an integer pointer, I'm taking a step that's 4 times bigger. I'm taking a 4 byte step as I walk through memory. Make some sense? I would say as a general rule, it always is a reasonable idea to make sure that your memory addresses are of the type that you intend to work with. That way you don't start getting partial values that were stored in memory. More modern languages solve this for you. There isn't, for instance, in Java and C#, there isn't a such thing as a void pointer. You got to have a type associated with it. All right. So you would probably always do something like that. Go ahead. So sometimes you might write a function that takes in generic memory. I mean, it would be for kind of specialized tasks where maybe the kind of value that's stored in there is more of like a kind of a blob value. It's not normal in types. It's like saying, okay, I need to store a megabyte of data. That's no known type. It's a void pointer that is a megabyte in size. So that just gives you that chunk of memory you can go and do stuff with. So it's kind of what's the right tool for the job. All right. Now, how many of you prefer that syntax? But it doesn't make you feel as cool. This one makes you feel like you're doing real geeky, techie stuff. Like, look, I regularly have conversations with the operating system. Yeah, you know, we're close. I just ask them to allocate some memory. It's all good. So most industry people would define the array like this. Because guess what? As soon as we jump to Java, you can't do this anymore. Direct allocation is no longer a thing. Instead, we get a real estate agent. We have this keyword called new.
Is that just for Java or is that in like most?
All languages, all modern languages. I'm going to say this is your real estate agent in charge of talking to the OS on your behalf to request memory. It always, put that in all caps, returns a memory address. Important piece there, because I'm telling you, if we went over to Java right now and I took that exact line of code, that's Java code. That's Java syntax. Works just fine. Most of our syntax here will work in Java, with the exception of this guy would become an int array fraction and an int array fraction, because we no longer have the special syntax for pointers in Java. They're still pointers, because like I just said, the new keyword always returns a memory address. And what's a pointer? Memory address. Therefore, pointers very much exist in Java. We just don't have special syntax for it, which is why I don't use any Java textbooks. At least nothing you have to pay for. It's a waste of time. There's better information in here, or at least used to be. We'll see what happens with that. All right. So questions, I'll leave this. We'll leave the cool kid version in there, just, in case you want to flex sometime. If you really want to get fun with it, instead of saying answer at bucket 0 equals this, what we would say is we would say answer plus 0 the value at that address is equal to the new numerator. Star answer plus 1 is equal to the common denominator. See, now that looks way cooler. It's like we're just doing memory math, right? You won't see that very commonly either, but that's more evidence of what I'm telling you is happening under the hood is in fact happening under the hood. This is saying go to the base address answer, take one integer size step through memory, taking us to bucket 1. Set the value at that address to this value. Make some sense? All right. Here, we'll leave those in there too. Okay. So now let's introduce something called a struct. This will be leading us up to our homework assignment. Let me hide this. All right. So we're going to call these guys a struct. I'm missing keys on the keyboard. A struct. Struct is short for structure or data structure. Now, we've seen that we can store our 2 parts of our fraction in an array, and we get to remember that bucket 0 was the numerator and bucket 1 was the denominator. Does anything actually prevent us from just deciding that we're going to say bucket 0 is the denominator and bucket 1 is the numerator? Could we just make it work that way because we like being difficult? Could we also just create a 10 bucket integer array and make bucket 3 the numerator and bucket 7 the denominator? We could do all sorts of crap that doesn't make any sense. And make sure if you do that, you don't leave any comments. So when you come back to it in 6 months, you're completely lost. You got to go walk back through your code and figure out what were you doing? What was I on? Oh, that was the whiskey night. I get it. All these things start coming back. But the point there is that we can pull it off, right? We're human beings, we're great problem solvers. I think I've mentioned it before. I like to think of programmers as kind of being like MacGyver. How many of you have seen the show MacGyver? I know they did a reboot that only lasted a season or something, but the original MacGyver, that was the guy, Richard Dean Anderson from Stargate SG-1. If you haven't seen Stargate, it's required viewing for computer scientists. SG-1 especially, but you should watch all of them, but you'll be disappointed in everything else. And the movie Stargate is mediocre plus, but the series Stargate SG-1, which is 10 seasons, is really good. But in any case, the idea of MacGyver was every single episode, he got himself in some sort of predicament, and he had to get himself out of that predicament using only the crap that's laying around him. Like, this guy was locked up in a garage. He built an airplane out of lawnmowers and stuff. Every episode was like that. So I've mentioned in here that when I give you a problem to solve, I want you to solve it in terms of the tools that are currently in your toolbox, what you have available to you, what's just laying around on the ground by you. Okay, that's what makes it fun. So what a struct does is it allows us to store multiple pieces of data that do not have to be the same type. So, for example, we can create a struct called player. And a player might have a string first name, a string last name, and an int, I don't know, jersey number, something like that. So we're storing 3 pieces of information about anybody who's a player, right? And those pieces of information have types, and but they don't have to be the same type, but they also have names. So no longer, if we were doing this as a fraction, so for example, if I come out here and I go ahead and I define, I'm going to say struct fraction. And we say a fraction has an int numerator and an int denominator. Like that. And then down here, we do something like struct fraction f1. And then we say f1 dot numerator is equal to 1. f1 dot denominator is equal to 2. Now, if I go and I print out f1, this will be the first thing that prints out. Oh, yeah. Oh, I misspelled struct. Oh, so in order to do this, so what it's yelling about right here is the C out with the little bracket things there doesn't know how to print out structs. If I want to show you this guy has a memory address, I can say the address of that dude. Oh, but I didn't do it as a pointer. Here, we'll just do this because this is what we really want. So f1 dot numerator. Oh, it's oh, I already have a variable's name f1. That's the problem. Here, we're going to say this is f3, f3. Call this guy f3. All right. So there is my 1 for my fraction 1/2. If I change this to f3 dot denominator, now I'll have my 2. Now, realistically, under the hood, these guys are stored probably very similarly to how arrays are stored. Probably in contiguous memory. How much memory do we need? Well, enough memory to hold 2 ints. If we were dealing with our example over here, we need enough memory to store a string, and an int. Strings are usually pointers, so we need a memory address, and 4 bytes. Okay? So that's what structs are. So now we have the ability to create variables of type struct. So I can say struct fraction f4, f4 dot numerator is equal to 1, f4 dot denominator is equal to 4 for our 1/4. And then maybe we want to go ahead and write a function for adding fractions. So I'll start us off here. This is going to be our homework. All right. So we're going to say we're going to have a function that's going to return a struct fraction called add fractions structs. And this is going to take a struct fraction f1 and a struct fraction f2. So in here, we're going to say, write the code needed to add f1 to f2, storing the result in a new struct and returning that struct back to main. Hint. Structs are passed by value by default, which means that when we pass something to a function or we return a struct, it behaves like a normal int rather than a pointer. That's not always good. Just, in fact, I might even say that's confusing, because I would make the argument that structs are kind of a evolution of an array at some level, at least as the way we're using arrays. And arrays are always passed by address. Yet structs are always passed by value unless we specifically use our syntax for passing in the address of a struct and returning the address of the struct. So we're returning a struct pointer. It works as a pointer. You just have to use the syntax just like we did with ints to make it work. In this case, you don't actually have to work with pointers for it. You could. In fact, I encourage you to do it, because next time we're going to be having it not return a value. Instead, it's just going to update fraction f1 to be the answer and go back. Go ahead.
You scroll up. You put a semicolon after the bracket.
Ooh, this guy? Yeah.
You do that after every struct.
When you're defining a struct, you actually do have a shorthand for this. So you can call this like my first fraction or something like that. And what that'll do is it'll actually give you already a variable of type fraction called my first fraction. It's like built into the syntax. You can define your first variable. I think it's stupid, so I would never do that.
The struct below is
This is my variable type. I'm defining a variable. Its type is struct fraction.
and then below main.
Below main.
Give a second struct. Put the struct half fraction struct.
Sure. What line?
Like 52.
52. Oh, yeah. So this guy, the return type for this function is struct fraction. That's the kind of value it's returning. I know it's unnerving because it's two separate words, but the kind of value it's giving us is a struct that is a fraction. That's what it's returning. As parameters, it takes in a struct fraction and a struct fraction. So that defines the entire type. Good news is structs go away when you get into Java, because we just use objects in place of structs, but there's going to be a rationale with that too. I'll give you the first punchline. The punchline is that we just said structs are all passed by value. Objects, classes are all passed by address. So Java would say, oh, you don't need structs. You can just do everything in an object. Oh, but it doesn't behave just like a struct. It behaves mostly like a struct. except it's passed by address by default. And remember, in Java, we can't undo that. We don't have a syntax. All right. So this is the homework for next class. I'll share this code up on Slack, and I'll also give you the link inside the homework assignment. So your assignment is to write this struct version of add fractions. Shouldn't take too long, but you're going to be working with this new syntax. All right. Questions, comments, concerns, bribes. All right. I'll see everybody on Thursday.